Hello and welcome to the Data Engineering Podcast, the show about modern data management. When you're ready to build your next pipeline and want to test out the projects you hear about on the show, you'll need somewhere to deploy it, so check out our friends over at Linode. With their managed Kubernetes platform, it's now even easier to deploy and scale your workflows, or try out the latest Helm charts from tools like Pulsar, Pachyderm, and Dagster. With simple pricing, fast networking, object storage, and worldwide data centers, you've got everything you need to run a bulletproof data platform. Go to dataengineeringpodcast.com/Linode today, that's Linode, and get a $100 credit to try out a Kubernetes cluster of your own. And don't forget to thank them for their continued support of this show. Have you ever had to develop ad hoc solutions for security, privacy, and compliance requirements? Are you spending too much of your engineering resources on creating database views, configuring database permissions, and manually granting and revoking access to sensitive data? Satori has built the first DataSecOps platform that streamlines data access and security. Satori's DataSecOps automates data access controls, permissions, and masking for all major data platforms such as Snowflake, Redshift, and SQL Server, and even delegates data access management to business users, helping you move your organization from default data access to need-to-know access. Go to dataengineeringpodcast.com/Satori, that's Satori today, and get a $5,000 credit for your next Satori subscription. You listen to this show to learn about all of the latest tools, patterns, and practices that power data engineering projects across every domain. Now there's a book that captures the foundational lessons and principles that underlie everything that you hear about here. I'm happy to announce I collected wisdom from the community to help you in your journey as a data engineer and worked with O'Reilly to publish it as 97 Things Every Data Engineer Should Know. Go to dataengineeringpodcast.com/97 things today to get your copy. Your host is Tobias Macy, and today I'm interviewing Davit Buniatyan about Activeloop, a platform for hosting and delivering datasets optimized for machine learning. So, Davit, can you start by introducing yourself?
Hey, Tobias. Thanks for having me here. My name is Davit. I'm founder of Activeloop. Before that, I was doing a PhD at Princeton University, where I was dealing with really large datasets at petabyte scale. And we had this process of running machine learning and deep learning on these huge datasets to reconstruct the connectivity of neurons. And we had to optimize, drill down a lot of stuff, and just creating datasets and maintaining them is a big challenge. And that's what motivated and helped me to start the company 3 years ago.
Do you remember how you first got involved in data management?
Yeah, so I had a task to train a deep learning model. And you think it's very easy to get started. The basic, like you get started with ImageNet, you have to train this classification model, try to get to the same results as, like, let's say you get on AlexNet. Problem with that is that I spent myself like 2 or 3 weeks just unzipping all the ImageNet files, getting access to it, wrapping up, and then make the format, get the data loaders correctly done so I can plug this into TensorFlow or PyTorch to train a model. And that felt a little bit slightly demotivating because I think that I'm starting a PhD to train models, but actually I spend most of my time on doing data engineering work. And things get worse when actually the data is not 100 GB, it's actually 100 TB size. And the times like most spent on actually looking into the data sets itself rather than trying to innovate on the model side.
That brings us a bit to where you are now with Activeloop, and you mentioned that you started it about 3 years ago. So I'm wondering if you can just give a bit of an overview about what it is that you've built there and some of the story behind your decision to build a business around this, to tackle this problem, and what it is about this particular problem space that is motivating you to dedicate so much of your time and effort to it.
As I mentioned before, when I was at the neuroscience lab, we overlooked into the training aspect of the models, focusing on models, getting them deployed efficiently and so on. But the challenge we had is that just processing a petabyte scale dataset on AWS was costing us $1 million. And our goal as data science and computer scientists in the neuroscience lab was to reduce this cost 2 or 3 times. And to be able to do that, we had to rethink how the data should be stored on storage, how it should be moved from the storage to the computing machines. Should we use CPUs and GPUs, and what kind of models to use? And this kind of insights helped us to think about what are the things that we can actually move this process and make it much faster, efficient, and more importantly for data scientists to take like less spend time on data itself, or like all this time that is kind of wasted and instead can be reused for more important stuff, and automating this process. And that's how we got into Y Combinator 3 years ago. We raised our seed fund, and we started working with early customers. One of the customers we worked with, they had 80 million text documents. And the problem was to train an embedding model, take this text data, put them into vectors so they can run a very efficient search later. The problem they had as a data scientist and data engineer in the team, just the training itself was taking 2 months. And we helped them to reduce the training time to a week project, cut compute and storage costs, and use much more complicated model that resulted in much better results. Another company of ours, Intellinear, they had aerial flights over the fields in Illinois to collect a lot of aerial images to be able to provide insights to the farmers. And the problem they had is that they had to identify where there's a disease in the field or dry down area. And they collect petabyte scale data put on AWS S3, and they have to train all these models. And we help them to be building all the data pipelines going from the unstructured to the models. And what we learned so far is that actually, the models is not the problem. You can get pretty good results. You can get up to plus 95% accuracy on the challenging problems that actually solve a real problem today in NLP or in aerial imaging on computer vision. But getting to that stage where you have this cycle of dataset creation and model training plugged into an organism that not only models evolve, but also your data sets, that's a big challenge for the companies. And even if you go and Google search today, give me a database for images, let's say, what you find out on Stack Overflow, they all say, hey, store all your data or metadata into a database and then point files or proxies to blobs to where the data is stored. And that's where you think, okay, there should be a database for, or at least kind of a data store for how this data should be stored. So it very efficiently plugs into machine learning use cases. And that's where we built an open source solution called Hub that helps data scientists to very efficiently represent unstructured data and then stream them to deep learning frameworks, more specifically now supporting PyTorch and TensorFlow to train those models and kind of rapidly evolve all these data set iterations.
And you're mentioning that one of the bigger points of friction is the specific way that the data is stored, because in analytical use cases, for instance, a lot of the data is stored as Parquet files, or you might be dealing with just these large image files that are optimized for human viewing, but not necessarily for machine processing. And I'm wondering, what are the areas of friction and the ways that the storage of the data can slow down the actual development process for machine learning workflows?
I was looking into a recent survey, and basically the survey starts is 1/3 of ML projects, they fail because you don't have a solid data foundation. And solid data foundation both includes the storage and also includes making sure the data is clean, making sure it's version controlled, and so on and so on and so on. So the problem is very big for the machine learning space as overall. And then you have structured data or tabular data where everything is sort of figured out. You have Parquet, you have version control, let's say you can do with Delta Lakes, you can use databases if you want high guarantees on asset transactions, and you have data warehouses, you can run queries at large scale. But when you go into spaces where the data is okay, I have a lot of videos, I have a lot of text data, you can now figure out with somehow using maybe MongoDB or other data source, but I have a lot of audio files. How can I query on this data? So, and all this gets into the fundament of, okay, what is the best way or what should be the way actually to store this data? So you can think of us or the solution that we are building as n-dimensional Parquet files. Instead of treating the data as to be okay, everything should be tabular. Now we treat everything should be instead of having columns in the table, you will have tensors in the columns, which are just n-dimensional arrays. I was recently talking to a professor at Berkeley. That's Berkeley came up with all this databases, and very interesting and non-intuitive things is he asked me, he's do you know what the best thing that is we are very proud of that we came up with over the 40 years is that we can store the data in tabular format. And then the rest is just a consequence of it. And the way we treat this is that, okay, what if we take the tabular format into a next level where we can also represent images or videos? And if you somehow think they're actually more structured data than the traditional, let's say, tabular data, but there are a lot of challenges with, let's say, you have to support dynamic shapes, you have to support varying sizes, as I mentioned, and how to efficiently represent them, any cloud storage location to stream them to a compute engine. That's later you can build actually a data warehouse on top or a database on top.
Treating the data as tensors in the storage layer obviously makes it much easier for the mathematical models of the machine learning process to be able to interact with it. And I'm wondering if you can just give a bit of a compare and contrast to what projects such as Pinecone are building with a vector database and any other movement in that space that may be coming up in recent years.
To my best knowledge, there are actually two branches you can think. When people say, "Oh, I'm storing unstructured data," there's vector databases, and there are also graph databases. They both claim that they are doing unstructured data, which is true in some sense as well. The problem with vector database, obviously you can take any tensor column and put them into a vector and then store it as usual. The most thing that they are very focusing on, and which is a big problem as well, is doing a very efficient search. So you have a lot of vectors. One first use case that we work with, we train a model to take all these text documents, all the patents, and then put them into vectors so it can put into Elasticsearch and then run a very efficient search on top. With graph databases, the problem is more on, okay, how can I represent this structure? It could be, let's say, in proteins, you have this million different graphs or social networks, so that efficiently I can generate insights from them. But none of them actually focuses on, let's say if an image, I put them into a vector, then I had, when I start to access this data and train a model on top, I have to somehow reformat it again to plug this into my ML frameworks. That's the difference that we actually, obviously there's some whenever you put the data on bytes, it's a one-dimensional array. But the way the models treat that, they think that this is very native. I think representing them as tensors is not anything new there. The main, I think, insight is that, hey, deep learning models, they take an input tensors, output a tensor. They don't really care if it's an image or video or maybe a structured data. So that's what they care about. And we thought that, hey, instead of actually having all this pre-processing done before the training process, why don't we do the pre-processing before we put the data into a dataset store so that then it can natively plug into a deep learning framework or any machine learning framework where you can generate insights. And then you can obviously use the same format to run a vector search. The graph representation will be slightly more tricky to do. On top of this, it won't be that very ideal, but it's still doable. And let the data scientists decide what they want to do with the data.
As I was going through the documentation for the Activeloop platform, I was noticing that a majority of your current focus is on image and computer vision workflows. And I'm wondering if there's anything about the specific needs of computer vision workflows and sort of the requirements in industry as far as that being a focus that led you in that direction versus using, any sort of focus on natural language processing.
So the first, everything starts is actually from passion. So I'm really passionate about computer vision and what it could be potentially helpful for problems we solve today. Self-driving cars, in agricultural, in medical imaging, and so on. Secondly, there's a big gap between computer vision has been just recently developed, last 5-7 years, and there was not a lot of infrastructure around the tooling so that you can build it. Another insights you can take from there is that, okay, now we are getting into this phase where we deploy, let's say, self-driving cars, we deploy a lot of robots and so on, that there's a big trend of generating a lot of unstructured data. And there's a huge challenge I'll say in machine learning as a whole, is how we can generate insights that are valuable and generate revenue. So far, extracting value from unstructured data, especially images or videos, it's actually a challenging business. You see all the excitement in self-driving cars, and all the IPOs you see there, but not many of them figured out the business model, how to generate revenue from it. Or not many of them, computer vision company startups, they're just getting started with figuring out, okay, how this is going to feed into the whole economies at scale. The challenge we see is that, okay, assuming that this, and we believe into that this market is going to be very big, they definitely will going to have this, the need for having a very, very good way representing the data, and there's no any current solution doing that. So that's where we can find our niche. But at the same time, the same technology could be actually used for structured data. We heard some interest from folks from our community that, hey, actually, you know what? I want to store this 500 GB of time series / tabular data on Hub. And we asked them, why do you want to do that? The problem with that is that I wanted to store with Postgres. Postgres, you have to pay, let's say, $500 per month on storing all this data in memory. And I need to be able to have much cheaper data representation, but at the same time, I want to have the querying capabilities they can run very efficiently on top. And that's where, okay, you can store this data on Hub, and then it actually sits on S3, so it's like 10 times cheaper in terms of the infrastructure cost. You don't have to store this data in memory, and you can stream the data to the computing machines as if this data was local to the machine. So you can actually benefit all the kind of querying capabilities given the use case that went very well. So having said that, with images, you won't store the data in memory. It's very expensive. And instead of having 500 GB data, you can have like 10 or 100x more data. And then the cost gets complicated. So nobody actually stores the data, let's say images in MongoDB, unless like the images are big. And then you go to the next level where, okay, instead of having just like, let's say full HD images, I have aerial images that are 50,000 by 50,000 pixels, or at least in the lab that I was working at the neuroscience, we were taking a 1 millimeter volume of a brain, cutting into very thin slices. Each slice was like 100,000 by 100,000 pixels, and we had 20,000 of those slices. There's no any format or solution that supports that. So that's why we, in the lab, we decided, okay, we can build this specifically for this specific use case. And that's where you see the biggest benefits actually once you deal with like large aerial images or biomedical images and so on. Yeah, that's like kind of a long answer to your question, but hope like I covered all the aspects that you were looking for.
Yeah, it's definitely interesting the amount of potential that there is in being able to let computers actually process and understand visual inputs because of the very sort of site-oriented nature of how humans operate and the number of activities that require some visual input for being able to interact with the real-world environment, thinking in terms of like robotics or self-driving cars, or to your point of biological imagery, being able to do research in terms of biology, particularly at the micro scale. Yeah, definitely very interesting problem area. So excited to see some of the ways that this can be used for that. And so digging more into Activeloop itself, can you talk through how the platform is architected and some of the optimizations that you've built in as far as being able to store and serve these processed data formats to be able to let machine learning workloads read in and process these tensors?
Let me get started with actually just going through very high level like kind of principles that we follow at Activeloop, and then I'll get into more like technological insights or the assumptions that we take to be able to do that. So the first one is that we have been strong on making the APIs very familiar to the data scientists, like having this NumPy-like or continuous pandas-like access to the data sets that feels very natural, and they don't have to go into the API reference for checking all the APIs. Like, can we give them a familiarity that they, in ideal world, when you're building a dev tool, you don't have to look into documentation. It's not the case, obviously, but that's like the dream where you get like similar to B2C apps. You don't want to look into the reference or manual. That's the first like kind of the target that we are looking into. The second principle that we follow is on performance. Like, how can we make sure that we continuously benchmark every line of the code to make sure that the hub is getting improved and optimized every time? And the third one is the extensibility. Can we make it such modular that hub can actually become the hub for the machine learning infrastructure? So you can easily integrate with labeling tools, you can easily integrate with computing tools or the cloud and so on. So those are the three main kind of like high-level principles that we follow. And let me get into more exact data architecture side of things. I mentioned like one of the keys is taking, let's say, million images into treating them as a single tensor of million by 512 by 512 by 3. It's more is that how can we lay out the data? Like essentially, if you want speed and performance, you have to figure out the data layout for specific use cases. And for our use cases, the top priority is training a model on the cloud where you can have either a single GPU or 100 GPUs at the same time accessing the data. The way we do that is goes against Hadoop ecosystem or MapReduce ecosystem, where you have to reload the data to each of those machines and then bring back the compute and then run the map and then reduce. And that's actually not working very well for deep learning applications as we see with Spark. Then can we store the data in a centralized location but give the same performance or guarantees for them? And what we found out is that if you have these three assumptions working properly, then you can actually guarantee this. The first one is obviously the network speed from the storage to the computing machines. We are still bounded by physics, like law of physics. So there's no way we can pass the speed of light. The second one is more we can have a control over is how the data is stored. How that like you take the data and then chunk them into storage. How you format each like arrays or the images onto chunks, and then how you represent that on S3. And the third one, which is very interesting, is this data obliviousness. which basically says that before I start the computation or during the computation, I can know the access of the data, of the pattern of the access of the data. So basically, I will know that I want to ask the first index, second index, and the third index of the images in a row. It could be like randomly shuffled. That's not the problem. But the problem is that I can use the networking to prefetch the data so that the machine thinks the data was local while it's running the computation. And if you have these three assumptions, what you can show, and that's what we do, is that you can have the data set stored, let's say, on AWS S3, but stream to the GPUs as if the data were local to the machine. So basically, for the GPU, that's most expensive resource, you have all this in your whole pipeline. It doesn't feel any difference reading the data from local SSD or actually streaming it over the network. And that's where you see that kind of the technological architecture there. That's where you isolate storage and compute. At the same time, they're like in kind of the symbiosis that they feel that they are very local to each other.
And then as far as the data modeling considerations for people who are looking to store their data in the hub, I guess, what are some of the pre-processing workflows for being able to start with a source image data set and then process it and store it into the Activeloop platform so that it is able to allow for arbitrary access into these different tensors, or being able to parallelize across the tensor arrays to do sort of multipath processing?
With a previous version of Hub, it was very tricky, but we have spent for the 2.0, spent so much effort on thinking how we can make it very simple for data scientists to be able to transform their original data. Currently, what you can do is you basically go and say, okay, I need these three tensors, and then let me just treat them as lists and then append all the data there, and then we'll do all the heavy work behind the scenes to make sure that we take correctly the data and then structure them. You can also use a feature that we just pushed actually today. It's called transforms or compute, which can actually parallelize this process. So you just define a Lambda function and then run over the data. But I think what's coming next few months is the single liner that you can point to a folder structure. We extract the metadata from how you store the data and then transform them automatically for you. And what we found out is, like in very naive terms, is that we can translate your format, so your data into our format faster than you can just copy on a Windows machine. Or like you can copy the data from a local storage to the AWS S3. We have been very focused on, because we felt that that could be a friction before, until this becomes mainstream. So once this mainstream, you don't have to anyway store like your original raw format data. But since we are doing this transition, we have to make sure that's very convenient and easy to use.
Another interesting element of what you're building, particularly with the Hub project, which is the open source library for being able to interact with these workloads, is that you do provide the Activeloop managed backend, but then also people can just use arbitrary object storage, whether it's S3 or GCS, et cetera. And wondering, what are the feature and performance trade-offs between those two options of self-managed storage locations versus what you're providing with the managed Activeloop platform?
We wanted to make it open source from day zero, so we don't like actually force anyone logging into our platform or manage it. So that's why we're like, hey guys, like you can use S3 or you can use GCS and Azure to store all your data. But at the same time, it's like, hey, actually we can do things for you that's much more efficient or that will make your life easier. So let's say if you use managed platform, you don't have to pay for the egress fee, and that's thanks to our partner Wasabi to store the data. So basically, data scientists who are not working at large-scale companies, this is a 4 times cheaper alternative to AWS, and without egress fee, that they can store their data and then train a model, let's say on Google Colab. Plays very nice with the community, with the researchers, and so on. But then once you go into like a scale engineering group or like a larger company, then they have to worry about security, compliance, like the encryption of the data as well, both in REST and the streaming process as well. And that's where our managed solution works, where the customer can point to, let's say, their own AWS cloud. But that's where we get into their internal VPC and then store the data and then stream that and make sure that the data never gets out of their hands. So those are the benefits for the managed system of Hub. But at the same time, we don't limit them. Like if you're like a company, you want to use Hub, but you don't want to work with us, that's really great. Feel free to use it, put into your S3 and then just point to your S3 and then start using it. And we have seen a lot of companies doing that.
Are you bored with writing scripts to move data into SaaS tools like Salesforce, Marketo, or Facebook Ads? High Touch is the easiest way to sync data into the platforms that your business teams rely on. The data you're looking for is already in your data warehouse and BI tools. Connect your warehouse to HighTouch, paste a SQL query, and use their visual mapper to specify how data should appear in your SaaS systems. No more scripts, just SQL. Supercharge your business teams with customer data using HighTouch for reverse ETL today. Get started for free at dataengineeringpodcast.com/hightouch. And then another interesting element of this data storage layer that's specialized for machine learning is that there are a number of workloads in different organizations where the same source data assets might be used for building and deploying a machine learning model, but also in an analytical context where you want to be able to gain some sort of business intelligence from those source data sets. And I'm wondering how people have been able to synchronize or manage these two disparate workloads where they might store their data as these preprocessed tensors in Hub, but then also pull, maybe some image metadata out of the source files into their data lake or data warehouse for being able to do analysis and then be able to feed back any insights from their machine learning models into those locations as well to be able to merge those different paths.
One of the features or requests that we heard recently, we don't have that now yet, it's like very high integration with Spark. So that you can, as you mentioned, get the metadata and push it and run on a Spark cluster and then get the insights there. Or let's say, is there a way we can synchronize or interface with data warehouse like Snowflake to pull the data into our format, train a model, and then push back a new metadata back to the Snowflake? So that's another integration. And what we are doing now is like we are kind of prioritizing on the integrations work that you can do, and especially with more traditional workloads in data warehouses or like the current data lakes that you use. So we kind of want to treat us not as an alternative, but more as a kind of combo where you also additionally have these capabilities of storing and very efficiently working with unstructured data. But at the same time, what we have seen and what we are looking for is like, can we make this whole process much more efficient, both familiar and also like efficient? And you can use new alternatives. Let's say another kind of integration we are doing with array or N-scale array, where you have the data in a distributed way storage and you have also distributed compute. Can you marry them? And that's kind of new ways of running the workloads. And that's where our primary focus is. After nailing down the format, can we integrate with the rest of the ecosystem, make it as simple as seamless to use? One thing that I want to stress out, you mentioned, is that, okay, I have all these analytics use cases. What's the best format for that? That's how Parquet or like all other like data warehouses like based on SQL queries have been based on. There's no anything similar for First of all, for machine learning in general, but also like in deep learning specifically. Or let's say, is there a way I can query on unstructured data like images? And the way you will do is that, okay, I have like, let's say, 1 million images. I want to find all the images that have a bicycle running in front of the car during the night so I can subsample it and maybe train a model separately. Is there a way I can run a SQL query on top of this and then generate the insights directly? Intel behind the scenes is that, I have a model that extracts the bicycle and the time during the day and so on. And I will run this models at scale very efficiently, get this metadata, and then push the subset of these images back to the user in a very efficient manner. And that's where we see this becoming next step is like, once you're nailing down the format itself, can we bring the data warehouse capabilities to this structure?
That also introduces an interesting question as to who are the majority users of what you're building with Activeloop and Hub, where in analytics use cases, there is a fairly well understood delineation of the data engineer is responsible for sourcing the data into the data warehouse. And then you might have an analytics engineer who's using dbt to build out the analytics pipelines to propagate into the business intelligence systems. And there's some overlap there. With Hub, it seems that the end user is largely going to be the data scientist, but that they still need to rely on the data engineer to be able to capture and organize the source image data sets. And I'm just wondering how you see the Activeloop platform and the Hub framework influencing or supporting the combined work of data engineers and data scientists.
So if you take the spectrum of, let's say, developers, on the left hand, you have the developers, and then you have data analysts, and then you have data scientists, and then you have machine learning engineers, and then you have deep learning engineers, and then the deep learning engineers are 10,000, order of 10,000. Machine learning engineers are order of 50,000, let's say. Data scientists are order of 100,000 to millions, and then data analysts go furthermore. And we took an approach is like, hey, let's heavily focus on the right aspect of the spectrum and make this work very well for this small group of people, so they don't actually have to like give them data engineering capabilities. For example, when I was starting with training models, I had to learn a lot about distributed systems. I had to learn a lot about how the data should be stored, like how to build all these data pipelines and scale before I start doing the training process. That's where I'm experienced at. So to be very efficient, you have to be a PhD essentially in distributed systems and in deep learning and machine learning. And that's kind of like, there are only very few people. Even us as a company, we're trying to build a tool. It's very difficult for us to find those people to join us to get started on this. And that's where our focus is on enabling the data scientists who work with a lot of images, don't interfere with data engineers, and let them be, like, give them the tooling that they can really very speedily work on the data. Even in your data scientist and you're starting with a project, you as a data scientist has to spend a lot of time as a data engineer in the project. And that's what we are eliminating, not the data engineers. And then data engineers can enable them to run much faster for their data teams. But this is all very, as you mentioned, is still like getting figured out in the organizations where they don't have all this kind of decided manner of how we're going to work with the data as they have with like analytics use cases, where the business unit pings the data analyst pings the data scientist, and then they get the, let's say, the integrations, the SQL query, the dashboard, and back to the business unit and so on. Like, this is not figured out in the unstructured world. And that's where we are kind of building the base for it. And then later, as we envision the company evolves and we get more usage on the adoption on the side of the format things, let's say, can we actually make this tool so generic that data analysts can use it? And furthermore, like, not only data analysts, anyone can just type a query in text, and then it uses GPT, let's say, transforms it into a query that is like native to the tensors, run any model that you need to add any the additional metadata, and then bring back the query to the person who was just looking for the disease on an aerial image. That's where our vision goes into, but like, we have to go there step by step.
Another interesting aspect of what you're building at Activeloop is that it seems to obviate the need for a number of different pieces of sort of data infrastructure and quote unquote MLOps infrastructure that has been gaining a lot of ground in sort of the very text oriented world of machine learning, thinking in terms of things like feature stores and different stream processing engines. And I'm wondering what you see as the potential for expansion of Activeloop into areas beyond just the vision oriented data sets and maybe potential integration with these feature stores, or whether those technologies are necessary in the world where all of your data is living as a preprocessed tensor for these machine learning workloads.
Not really. Like, let's say, is there a Kafka for unstructured data? Or is there, like, can we take Tecton and put it into images as well? So the problem with Kafka, let's say, is that, hey, if you have like a million mobile phones and all of them are streaming videos, is there can you actually use Kafka or somehow like any streaming processing to store this data? There are some core fundamental architecture changes you have to do there to be able to enable video processing, let's say, because you have to minimize the copies basically of the data, like eliminate all of them, get to the storage format. So, but then there could be a potential symbiosis where you can take what we do at Activeloop, combine with what Kafka has, and then, hey, now you can actually stream like million videos to data lake or data store, and then stream them then to do a training process on top, or do like there's a feature store, but then you can actually version control all the deltas of your data. Having said that, which means the way we do forward is that, hey, if we can do an integration and that enables the data scientist or the end user much more efficiently, rather than us building this whole functionality, which is very complicated itself, then it's better to run the integration. But then when we see those technologies need to do a core fundamental change, they also will be very reluctant to change their core to support additional types of data, unless this need is very big. And that's at least observed with Databricks as well. So having said all this, we really want to work with other both open source and non-open source projects to expand the capabilities of and how the data for unstructured data specifically can be stored and then streamed, processed, like from, let's say, a million cameras all over the world. And at the same time, like, hey, this is going to change another core functionality or core architecture, then maybe we can have an alternative to that and then build it quickly.
You mentioned earlier that you currently integrate with PyTorch and TensorFlow as far as the hub library and the platform integrations. I'm wondering what would be involved in expanding and generalizing the support for other machine learning frameworks and other language runtimes to be able to take advantage of the storage and interface optimizations that you've built at Activeloop?
So with other deep learning frameworks, it's so more or less it's sort of straightforward. Like let's say we have the MXNet interest from few folks from the community. Then can we actually take this and then put it into more like the traditional world where can we integrate this with XGBoost or LightGBM or other ML training frameworks? And that should be very straightforward as well. Though, like we would like to specify is that most of the benefits come actually because the data is unstructured. So that's where like the streaming and optimizations can come into the place, the assumptions that I mentioned before. But at the same time, yes, that's like totally possible. And given the interest, we can start like pushing more engineering resources on optimizing those use cases. So if one day comes and like, let's say that, I don't know, like XGBoost is the most useful use case for Hub, then we'll put all our efforts to make sure that this use case can be supported as optimized, as efficient as possible for those users. They are like kind of more like if you nerd out here, like from the research I remember at Princeton, they're like more RAM limit memory algorithms that take into consideration that, okay, I have like very limited amount of memory that I can store the data locally, but I also have huge data. So I can just run, let's say, training on a single model. And that's what we want to envision for models. They see the whole data at the same time, but they abstract away basically from the compute limitations they have.
As you have been building the Activeloop platform and building this open source ecosystem around it, what are some of the most interesting or innovative or unexpected ways that you've seen Activeloop and the Hub framework used?
The one use case I mentioned before is that, hey, actually we can store this data instead of storing in Postgres DB, which was like kind of surprising. We were not optimizing for that. We were optimizing for something else. That was slightly interesting, but I wouldn't call it as unexpected as in terms of the challenging lessons that we learned, and we learned a lot of stuff, and especially when with our first iterations, we didn't pay much attention to the user experience, and the users had to specify a lot of parameters to make sure that the storage itself is like performing as we intend to them. Like, for example, one benchmark we run is that, hey, what if one of the customers asks us, the data could be stored in, like MongoDB starts supporting aerial images. What are you going to do? And then we take MongoDB, we push a very small data set, like a couple GB data set to the MongoDB, and then we take the same data set, push it into Hub on S3, and then train a model on top. And what we show there, we can actually get the same performance as the MongoDB, but without any without any database or without any in-memory cluster machine that sources data while you're training the model. For the Hub 1.0, it took us 20 minutes to spin up MongoDB, and it took us like 8 hours to fine-tune Hub to make sure the performance as we wish. We know as the developers we're using that. Now with 2.0 is that we removed all this complications and make it very simple to use. And because of this, we actually took a lot of core assumptions in the data layout that you will then see in other like similar or maybe other like products that or like open source tools that we took for. And those assumptions in data engineering, like they have consequences, and those consequences like then alter all the architecture you're going to build later and so on. So you have this butterfly effect on making a core architecture decision on like how single bit should be stored, that impacts the rest of the like follow-up, like getting into like more like end of the pyramid of all the data. So I think that's very interesting. You get into this limitations of cup theorem in databases, then how to guarantee all the things that you want data scientists to have, but then you're going to have a lot of trade-offs to do. That's from technological things perspective that the professor at Berkeley mentions, like essentially they're just getting started both in Stanford and Berkeley to research on this topic. So it's like you nail down the databases for structured data, like data warehouses and so on. But for unstructured data, this is just getting figured out in research. Nobody has yet started publishing papers. And it's kind of a challenging problem for a startup to solve. But because usually what you see is that either you already have a well-established paper or published project, and then you take this into a market, but you don't innovate during the startup. Like you do it much later stages, or you build a like mobile application, B2C something. That's the kind of, I'll say, a challenging lesson we learned. Yeah, we are trying to figure out how the best we can combine both the innovation and also like the kind of business requirements for building a sustainable business on top.
It's definitely a very interesting problem space. And that was one of the things I was noticing as I was getting ready for this interview is that you went straight from your PhD program into this business. And I imagine that that brought in a lot of interesting complexities and challenges and learning curves beyond just the technological problems that you're trying to address.
Yes, in that case, Y Combinator was very helpful, like kind of re-brainwashing us from the PhDs to the founders. I myself still have this problem, like still think too much, too complicated. And there are certain things you can do so snappy, like without getting into very far and like building all the end-to-end perfect. It could be a product, it could be like a plan or strategy or the sales motion and so on. Just like, how can you simplify all this? Like, how can you simplify such that anyone can understand what we are doing? And we had this problem from the day zero. And we are still like in this process, okay, how can we simplify and communicate with people like the benefits or the value propositions that we do who are not actually doing data science or like general people who are not in the domain. And I feel that that's one of the things that's challenging from you're coming with this all the technical background, but that becomes a limitation for you to be, let's say, in a podcast like this to talk to more people.
You may have already touched on this, but what is the most interesting or unexpected or challenging lessons that you've learned while working on Activeloop and building out the technology in the business?
We have been very focused on the technology, and technology is not the main decide. I mean, it's very important, obviously, for such a company, but there are also other aspects you have to nail down, including the product and sales. Number one lesson that we learned, I think it was at Y Combinator, is that in B2B, better sales mean better technology. You want to have good both of them, but you also have to pay focus on talking to the customers, learning their real needs, and instead of like taking this, oh, this is a challenging problem, let's try to figure the solution for it. And I think that's the biggest lesson for technologists, to listen to the customers, to learn from them, and then iterate on the feedback rather than on the internal insights. Though sometimes you have these exceptions which are great that actually work out with your insights, but that's like the probability is much less than taking the input from the environment.
And for people who are interested in being able to optimize their machine learning processes or they're dealing with computer vision workloads, what are some of the cases where the Hub and Activeloop platform are the wrong choice?
Essentially, initially the problem was that if you have like very small data, like you have image size, like which is 28 by 28 pixel images, then you can actually store in a usual database and like a more structured form. And we haven't yet super optimized for the use cases. So that's like kind of a flag to be upfront. Our main kind of benefits come into the place when your data sets become bigger. Like start seeing the benefits when you have more than, let's say, a couple hundred GB data sets. Like the real benefit, like the threshold I will say is that, hey, I no longer can store this data on my local machine or virtual machine on the cloud. I have to copy this data every time I start a training process. That's where, hey, like you can use Hub actually to not waste any GPU cycle or any compute cycle or your time to copy this data there. So that's where our benefits come into the place, and they shine when you have petabyte scale data sets. Though currently 2.0 is not yet scalable to the petabyte, and we are working towards by the end of the year. But that's where we see ourselves nailing it down for larger use cases.
As you continue to build out the technology in the business, what are some of the things that you have planned for the near to medium term and any projects that you're especially excited for?
I think the main core focus for us now is to really get Hub adopted in organizations who are working with unstructured data sets, especially images or videos or audio coming soon and text as well coming soon. One thing that we think is that this is going to take into is actually letting users and data scientists to be very easily to navigate through the data. And this navigation comes into two forms. First of all, being able to ingest the data as a human being so that you are able to visualize the data. And it could be really huge data sets, it could be small data sets. Think of like Google Maps, but for actually any n-dimensional data. Or like, I don't know if you've seen the movie Interstellar, like the last part where it gets into a black hole and you have all this 4-dimensional data. Can you actually give very easy tool that we are working on to visualize all this like complicated data sets and their combinations of them? The second capability that we have been working towards and thinking that this could be very useful, though it hasn't been proven yet, is that how I can query this data, how I can process this data? Like, can I quickly search, like the way you do Google search on the whole internet, can I actually search over all my data and also like instantly visualize this? In Iron Man, you have all these capabilities of being quickly locate the target you're looking for and so on. I mean, it sounds futuristic, of course, but if you nail down to the use cases you have with the companies and what they're looking for, that's where we see the most impressiveness is coming into. Our bets are into, okay, can we make like Snowflake for unstructured data? But then you also need basically Tableau for unstructured data. You have all these other tools. Either there will be other separate tools that will develop software and we can do an integration, or can we make this end-to-end user experience very seamless and easy to use such that anyone, only data scientists, can use it.
Are there any other aspects of the work that you're doing at Activeloop and the overall space of dealing with unstructured data and optimizing for machine learning that we didn't discuss yet that you'd like to cover before we close out the show?
I also love to mention that we also have a podcast, Humans in the Loop, where we invite different CEOs of companies who are AI core. So basically they build AI applications, and we talk to them about their challenges they have, both from the business perspective and from the technological perspective about the data. We also have a Slack community, and you can go into slack.activeloop.ai or hit me on Twitter at Davit Buniatyan and follow like just our journey on Twitter at Activeloop.ai. I feel like what we're looking for is that more people joining into the community, giving us feedback, their thoughts, how we can take the direction and what are the main problems they are seeing that we can help them to improve, and maybe also welcome the contributions from the open source side of things. So that's like kind of a high level pitch here to this community.
Yeah, I'll add links to all that in the show notes. And for anybody who wants to get in touch and follow along with the work that you're doing, I'll have you add your preferred contact information there. And as a final question, I'd like to get your perspective on what you see as being the biggest gap in the tooling or technology that's available for data management today.
So every person listening to this podcast basically knows that dataset management is not that easy. In fact, it's like a big pain to process it and like to solve those challenges and build up data pipelines and do all these problems. But inside, we all feel like, oh, I want to go to train this model. I have to fine-tune the architecture and deploy this model into the production. But from the other perspective, to get better predictions, but get better models, like there's not that much you can do after like you went through all this like a kind of autonomous stages for the model itself. And we feel that the community and the researchers have shown very great results on the models themselves. But because of this, we kind of lost the data-centric approach that we had, let's say, 30 or 20 years ago, 10 years ago. And we have been too much focused on the models, but less focused on the data. And not just the data itself, like treating as data sets as living organisms. As you have like software 2.0, where the software or the code generates another code to be able to solve the task, we feel that the same should be as well done for data sets, where data sets are organisms that they grow, they expand, they like the models learn from the data sets and then generate more data out of it. And then you can have data 2.0 with software 2.0 in quotes, and essentially without the cost of the data scientist's brain power solving these problems.
All right. Well, thank you very much for taking the time today to join me and share the work that you're doing at Activeloop. It's definitely a very interesting project and an interesting problem domain, and definitely excited to see more projects and companies building out more optimized formats for simplifying the lives of data scientists and deep learning engineers. So appreciate all of the time and energy you've put into that, and I hope you enjoy the rest of your day.
Thank you very much, Tobias, for the invite. Really great chatting with you.
Listening. Don't forget to check out our other show, podcast.init, at pythonpodcast.com to learn about the Python language, its community, and the innovative ways it is being used. And visit the site at dataengineeringpodcast.com to subscribe to the show, sign up for the mailing list, and read the show notes. If you've learned something or tried out a project from the show, then tell us about it. Email hosts at dataengineeringpodcast.com with your story. And to help other people find the show, please leave a review on iTunes and tell your friends and coworkers.
La 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 la